Okay, welcome back, everyone. Welcome to the second session of today. Today we're going to be hearing from Teng Liu, who's also from the Max Planck Institute in Germany, who's going to be telling us about using BXA on eROSITA data. So, Teng, the floor is yours.
Okay, thanks. Good afternoon, everyone. This morning, Johannes has introduced to us the Bayesian spectral analysis method BXA, and now I want to show you an example of using BXA. That is the actually spectral analysis in the eROSITA eFEDS survey. First, I want to show you two photos of eROSITA. On the front side, there are 7 identical mirror modules. And on the back side, there are 7 almost identical CCD cameras. The major mission of eROSITA is to scan the sky for 4 years. The scanning strategy covers the full sky in every 6 months, so that in the 4 years, it will scan the full sky for 8 times. Ahead of the 4 years scanning, we've performed a mini survey in this eFEDS field. The scanning strategy is like this. The pointing direction moves up and down and from right to left. And in a 4-day scanning, it covers a large region with an area of about 140 square degree. And it reaches a depth of 2.2 kiloseconds, which is even deeper than the 4-year all-sky survey. So as you can see, the image quality is very good. In such a small region, there are many sources. The image resolution is similar to that of XM Newton. This is about the eFEDS region. With the eFEDS field, we obtain a large catalog. Here, I want to compare the eFEDS survey with some other surveys in the space of the softband flux limit and area. So let's put aside the full sky survey for now. In this space, these dotted line correspond to catalog size. So with larger area and lower flux limits, it will lead to larger catalog. These two surveys, the FOXM and the Chandra CSC2, they are based on the full archive of XM Chandra. So they are not about selected contiguous region. Some famous contiguous region survey like the Cosmos field, the XM XL field, they are here in this region. The eFEDS survey is much larger than them, but it's not as deep as them. So eFEDS, basically, generally speaking, is a large but shallow survey. Another characteristic that I want to point out about the eFEDS survey is that it's softband dominated. As shown in this figure, this red line, this is the effective area of eROSITA. In the softband between 0.5 and 2 keV in this region, it has a large effective area. But above about 0.2 or 0.3 keV, there's a big drop. So as a result, in the eROSITA data, there are much more signal in the softband than in the hardband. And the selection would be more of a softband selection. I want to introduce to you about the eROSITA spectral data, since it might be helpful if you want to work with eROSITA spectra sometime. Here is an example of a source. Here is a point source. We draw a white annulus region to extract background for it, and any detected sources are excluded. Basically, the eROSITA spectra are the same to that of XM Newton or Chandra, but we need to pay attention to the fact that in the scanning mode, the extraction region is not always in the field of view. Instead, it moves across the field of view. So the exposure time starts when, let's take this big annulus, for example, it starts when it starts to enter the field of view, and it ends when the other side leaves the field of view. So as a result, the exposure time of this region is larger than the effective exposure depth at this position. for the source, we use a small extraction region, and for the background, we use a large region. So as you can see clearly that the larger region always enters the field of view earlier and leaves the field of view later. So it has a longer exposure time. To make sure that the source and the background are observed at the same time, we use the exposure time, the good time interval for the source to extract both the spectral force of the source and background, so that they will have exactly the same exposure time. We have seven telescopes. Each spectrum is extracted from each of the telescope and then combined. So the exposure time is averaged among all of them. Another important parameter is the extraction area. Because the extraction region is not always in the field of view, when entering or leaving the region, only a part of the region is in the field of view. So that after averaging in the whole exposure time, the effective area is actually smaller than the geometric area. So this is the backscale, which can be used to rescale the background spectrum to the size of the source extraction region. It is also averaged among all the activity telescopes. Since we are using an annulus region to extract the background, we consider that the source and background have the same responses. Therefore, we only extract the response for the source. And in the source ARF, similar to that of XM Newton or Chandra, we apply a vignetting correction and also PSF correction. In addition to that, we also apply an area correction, which corresponds to the difference between the effective area and the geometric area. This exposure time, it is only meaningful here for the spectrum. It's best not to use it anywhere because it must be used together with this RF where this area correction is performed. After extracting spectral for each of the telescope, we average the ARF weighted it using the exposure time among the 7 telescopes and then multiplied it by 7, assuming all of them are activated. And we average the RMF weighted by the ARF and exposure time. So this is about the eROSITA data. About the eFEDS field, in this large but shallow region, we detect a large catalog of about 28,000 sources. But here, we show the source net counts extracted from the spectrum. Blue means source, and the orange is for background. As you can see here, the value, about nearly half of the sources have less than 10 net counts. They are very faint. So is it really meaningful to do spectral fitting for such faint sources? Generally, I believe we would not do that. But in this work, in order to understand both the data and the method, we perform a systematic spectral analysis for all these sources. For the spectrum, the Bayesian method does not really require a rebinning of the spectrum. But since these sources are faint and narrow features, either absorption or emission features are actually irrelevant, so we group every 4 bins into one, just in order to speed up the fitting. All these analyses about the eFEDS actually spectral can be found in this paper. Before fitting the spectrum, we first model the background. To model the background, here this figure shows the background shape of the eFEDS data. To model the background, we first perform a principal component analysis for all the background spectrum in the eFEDS region. It gives us a few PC components, and then using these PC components and a few additional Gaussian lines, we fit each of the background spectrum. Here is an example. The red points, they are the background spectrum. We first fit this spectrum, and then we freeze the shape of the spectrum, only leaving a normalization. And this background model is rescaled using the backscale to the size of the source extraction region, which is the red dashed line here. And then it is added to the source signal, which is the blue dashed line. And then at last compared with the source spectrum data. So this is how the spectral fitting is done. Notice here that we model the background in the space of channel instead of energies. This is because we have the same responses for between source and background. Therefore, the only conversion we only need a constant conversion factor, which is the ratio between the backscale to convert the background model to the source region, so that we skip the step of convolving with response files in order to save some time. And for the AGN model, of course, we use the simplest absorbed power law model. We fix the galactic column density, and for AGN column density, we adopt a log uniform prior between 4 times 10 to the 19 and 4 times 10 to the 24. And we also, for gamma, we all adopt a Gaussian prior centered at 2 and with a sigma of 0.5. To model potential soft access, we add blackbody components. We adopt a temperature prior, a log uniform prior between 0.04 and 0.4 keV. Alternatively, we use another model to model the soft access, which is a power law model. This is a completely phenomenological model. Note that for the essential parameter, that is the condensity and the power law slope, we adopted broad priors. This range down to 4 times 10 to the 19, which is lower than galactic absorption. It is impossible to be measured. Up to 4 times 10 to 24 in the common 6 regime, it is also impossible to measure such thick condensity using simple power law model. And also for gamma, we adopt a very wide Gaussian distribution, which is much broader than the intrinsic scatter. So we adopt such broad priors in order to cope with the different types of sources in such a big sample. But we want to remark that a broader prior is not more correct. It is actually not true. Then input the prior and the data to BXA, it will explore the parameter space, and at last it gives us a sample of points. Each point is a set of the spectral parameters. Let's take an example. This source is fitted with a power law model, so it has the power law slope gamma, the condensity parameter, the power law normalization, the background normalization. We have this posterior sample, and we just plot the distribution of this sample. We can get the posterior probability distribution function for each of these priors. And actually, we can also see the degeneracy between these priors, for example, between condensity and power law slope. In addition to the PDF of each parameter, we can also plot the PDF for any inferred value, like flux or luminosity predicted by the model. However, a PDF is not easy to use. For a catalog, we still need to report a value. Of course, the most important value would be the median value measured from the PDF. Also, we can provide a measurement of the uncertainty. One method to calculate the uncertainty is the equal to interval method. In this case, below the lower limit and above the upper limit, the PDF covers the same area. This method has an advantage that it remains the same when converting from linear space to between linear space and log space. Another method would be the highest density interval. In this case, at the lower limit and at the upper limit, we have the same probability. It is also useful in some cases, as I will introduce below. As I said before, most of the sources are so thin that we do not expect to extract any spectral information from them. Actually, in fact, some of the very thin sources might even be spurious sources, as shown by simulation. And so, how do we know whether we are gaining real information from the data? We use this parameter. It's called the KL divergence. It's defined like this. it can be considered as a comparison between the input prior distribution and the output posterior distribution. So here in this figure, we plot the measured column density, the median value, as a function of this KL divergence. I've divided the sample into three subsamples. In this figure, I show a few examples of the PDF. Here, this blue, black line, it's the constant, which is the log uniform prior that we adopted. In some cases, when we have a really small KL divergence, it means an example is shown here with this cyan PDF. You can see it's similar to this this flat line. In this case, since they are similar, this value is small. And as shown in this figure, with a small KL divergence value, there's always very huge error bars because there's no information from the data. What we obtain is just what we input as prior. For a second class, as an example, this green PDF, it is different from the input prior. As complexity decreases, it increases, but it does not decrease again. So we cannot really measure HDI lower limits. In other words, as shown in this figure, these sources, their lower limits are always pegged at the lower boundary. So in such cases, the median value is not not really a good measurement either. So what the only thing that we know about these sources is that they are consistent with being unobscured. So what we call this class as unobscured sources. And here, the red one shows a case in which both the upper limits and the lower limits can be well constrained. In such cases, we call them well measured. We can safely use the value predicted from the PDF. And at last, there's a last class, an intermediate class, which is shown as this orange PDF. You can see it has a peak, but when it decreases slightly towards lower complexity, but has a long tail. So we call them mildly measured. So at last, we divide all these measurements into 4 classes. Only in such cases where we have a lower measurement of the lower limits, we can really use this is a minimum measurement of complexity. In some cases, the complexity is actually unmeasurable. There are 2 reasons. One reason is there's no information from the data, and the second reason is the source is intrinsically unobscured, so we cannot really give a measurement of the complexity value. Similarly, we can do a similar analysis for gamma. This figure shows the distribution of the gamma measured gamma value as a function of the KL divergence. Again, I divide the sample into 3. Here, these sources have the largest error bar, and these ones have the smallest error bar. So when there's a huge error bar, most of the sources have small KL divergence. And when we can have a good measurement, there's always a large KL divergence. Similarly, also in this figure, I show the PDF of a few examples. Again, this black line is the prior that we input. It's a broad Gaussian distribution. And this pink PDF is from a source, a very faint source. As you can see, it's similar to the input. So we get no information about the slope. And also, I plot 3 sources which have a large KL divergence. For this one with a solid line, you can see it's different from the prior because it's much narrower. And for the other 2, it's different because there's a significant shift of the center. So these are the 2 reasons causing a large KL divergence, either a small uncertainty or a center offset. In this distribution, we can see 2 branches. There are many sources located, especially in the upper branch, where they have a steep slope. It's because the soft access component is not modeled. In this case, the spectral model is just a generous slope of the broadband spectral shape. Then, since we have a measurement of the median value for complexity and for the power law slope, we can make a plot of that distribution. These colored histograms show the median distribution. But what I want to point out is that such a distribution is meaningless, because we know that in many of the sources, there's no information gained from the data. What we are obtaining from the posterior is just the prior that we input. Therefore, we need the hierarchical Bayesian modeling method as introduced by Johannes this morning to recover the intrinsic distribution. That is, we assume a parameter distribution at the sample level. So all the sources in the sample follow this same distribution. And it can be a Gaussian model or just a histogram. Then we use all the sources to constrain this model. So the result is for the condensed distribution is as shown by this blue histogram. As you can see here, actually there is a strong peak near at the lower boundary. They are unobscured. And above 10 to the 22, the obscured fraction is actually very small, only a few percent. Similarly, for gamma, we can measure the intrinsic distribution, which is much narrower than our assumption. Such a small obscured fraction is actually caused by sample selection bias. As I introduced before, the user data is actually dominated by the softband. So a softband selection favors softer sources. Here, this figure it's from simulation. It shows the detected fraction of sources as a function of condensity. So obscured ones are mostly missed, cannot be detected, while the soft sources are generally detected. So in the Bayesian hierarchical Bayesian modeling method, it does not correct for such models selection bias, sample selection bias. The selection bias is still kept in the result. And we also, since the Bayesian method calculates Bayesian evidence log z, we can use this value to compare different models. Here, this figure, it compares the APEC model and a power law model. Based on the property of the multi-band counterparts, we divided the sources into AGN, which are the blue sources, and the stars, which are the orange ones. We can see that some stars show a large difference between these two, with they favor the APEC model rather than a power law model. And some AGN favor the power law model instead of rather than the APEC model. However, notice this strong peak. Most of the sources are actually here near zero. It's because of the low signal-noise ratio. We cannot really distinguish between these models. To model potential soft access components, we added a second power law component. Here we compare the double power law model with a single power law model. And with this comparison, we can select these sources above a threshold. They favor the double power law model over the single power law model. We can see that in these sources, the soft access component is detected. In this work, we actually used a few models based on the power law model, which can be considered as a phenomenological description of the general broadband shape. We add a soft access component. This power law component can be considered as a physical component correspond to the inverse quantization in the hot corner. But this model would be problematic in the cases of obscure sources, since in the soft band, when there's strong absorption, there would be strong degeneracy between the soft access emission and absorption. We can also use even simplified version with stronger priors. For example, we can fix the power law slope, leaving the condensity free, and we can even fix all the parameters using a fixed shape spectrum. In this case, it is similar to what we generally do in actual catalog. We assume a power law spectral shape and convert count rate into flux using a value called energy conversion factor. In such case, actually, there's no spectral shape information. It's more of a count measurement. Obviously, all these models are wrong, but they can be useful in some cases. Maybe a more correct model would be like this. We should add a power law component, soft access, code reflection, and maybe even iron line. And we need to optimize the prior for each of the parameters, and also consider the correlation between these parameters. It would be hard, and maybe it can only be done for a particular type of sources. Okay, so at last, I want to show you a comparison between the flux measured through Spectral and in the catalog. In the catalog, we have a flux measured based on the image. I call it an imaging flux. It is as I just said, we assume a spectral shape and then use an energy conversion factor to convert count rate to flux. The count rate is measured also by fitting. It's similar to spectral fitting, but it's just the image fitting using a PSF model. And in the fitting, particularly for this the case of the eFEDS, we use the C statistic. So here we also use a shape fixed model. We are using the same model, the same data, but in the imaging flux we use the C statistic, and here we are using a Bayesian method. So here is a comparison of the flux method. I divide the sample into two. The brighter ones with at least 10 counts are plotted in red, and the faint ones are plotted in blue. So comparing the measured flux and also the errors, they are basically consistent. But in the case of the faint sources, as shown here, this is the ratio between the spectral flux and imaging flux. So the imaging flux measured through C statistic, this likely concentrate near the value, actually near the detection limit. But with the Bayesian method, it is allowed to go deeper, to go lower. Also for in the case of error bar, this is the upper error bar and lower error bar. The error bar measured through statistic likely pegged at some value. And using the Bayesian method, it would be allowed to go much larger. This is a difference. And since it is we always do this assuming a fixed spectral shape for an actual catalog to measure a flux. We also make a comparison to check how does the spectral shape affect the flux measurements. So here it's a comparison between the flux measured using a shape fixed spectral model and with a free shape spectral model. Here this is a ratio between the two different bands. It can be considered as a hardness ratio of the spectrum. And here this is a distribution of the fluxes measured using free model and the shape fixed model. So we can measure a scatter. This is a scatter that that is underestimated in the flux measurement of actual catalogs. Okay, that's all I want to say. Thank you. Thanks.
Thank you very much, Teng. Do we have any questions in the audience, first of all? Got time for a couple? Yeah.
Thank you very much. Just as a clarification, when you're talking about strong priors or weak priors, if I want to compare a model, so is someone, I mean, do you suggest to start with a strong prior or you just basically classify the type of priors? I mean, if I want to compare a model, would you recommend to start with a strong prior or to have a strong prior? You see what I'm trying to say?
You see, here in this work, we do not really, we cannot really choose a model for each individual source. We adopted a few cases. We adopted a few cases with different levels of priors, and we just simply report all the results in different cases. This is because we believe all of them are clearly wrong, and they can be useful only in particular for particular aims. For example, when we want to have a measurement of the property of the hot corner of AGN, we need to consider the soft access components.
Exactly.
And in the very faint cases, although we know it's clearly wrong, this model could still be useful to give a rough measurement of the of maybe luminosity, since as long as we keep in mind that it's based on a strong assumption.
Okay.
So, and I would believe a better way would be adopting more optimized prior for all the parameters.
Okay.
That would be hard and only feasible for a special type of sources.
Okay, thank you very much.
Everyone online, I believe.
Hi, Teng. So that was a very nice talk. I was curious. So as you said, the obscured fraction is obviously difficult to constrain because this is soft X-ray selected. I was just wondering if you plan to, or if it's even possible to maybe use the ArtXC data to maybe somehow predict or quantify this selection effect against obscured AGN in some way.
Generally speaking, I would say it's not really useful to the ArtXC data is not really useful since the number of sources detected by ArtXC is too small compared with eROSITA. eROSITA would detect millions of AGN across the sky, but ArtXC can only detect a small number of really bright sources. And to recover the intrinsic distribution of AGN's condensity, it is actually a different question other than other than spectral analysis. It is about sample selection. Actually, it can be done through simulation, like I shown here. This is a detection fraction from measured by simulation. We can make a correction using this result to recover the intrinsic property of AGN. But it would be better to use harder band data like from XM or Chandler, since the bias is in the case of eROSITA is too strong.
Mm-hmm. Yeah, okay. Thank you very much. And one more question, if I may.
Alternatively, we have a hardband selected eROSITA catalog. That catalog would be very, very small, but it would be less biased.
Sure. Thank you. One other thing. So you mentioned potentially including Gaussian lines to see if there was any ion emission in the sample. I was just curious. Do you know roughly like some sort of a number of sources that have you looked at how many sources might display ion features in their spectra in the
not really. Since most of the eFEDS sources are too faint, basically speaking, it's not promising if we can detect any ion line. But maybe it's worth trying for the full sky EROS catalog. There might be some bright sources.
Right.
It's worth trying.
Thank you. Okay.
Yeah, I think we better move on. So let's thank Teng again. Thank you very much.
Thank you.